Welcome. This video is going to go over the key for the Chapter 1 reassessment. So question number 1 asks how many hydrogen atoms are contained in 1 mole of ethanol. And so since they tell you have a mole's worth, you have to first look and see how many hydrogen atoms are in 1 molecule. And looking at the formula, you should see that there are 6 hydrogen atoms in 1 molecule. And then, of course, there's 6.02 times 10 to the 23rd of anything in a mole. So when I multiply the 6 times 6.02, that's how I came up with my answer of 3.6 times 10 to the 24th. Question number 2 asks, it says the empirical formula of a compound is C2H4O. Which molecular formulas are possible? So what you have to do is just count up how many of each, rewrite these formulas. So the first one is rewritten as C2H4O2, so that's not a ratio of the empirical formula given. C4H8O2 is simply the doubling of that, so that is C4H8O2 is also the simpler formula for number 3. So C2 and 3 are both whole number ratios of the empirical formula. Number 3, this is probably one of the most common questions that IB asks in their tests, and it's where you're looking at the stoichiometry of some kind of reaction. Neutralization reactions are very common. So again, write a balanced equation. What volume in centimeters of 0.2 molar HCl is required to neutralize 25 centimeters cubed 0.2 molar BaOH2? So my balanced equation is going to be 2HCl plus the BaOH2, and it will yield 2 water molecules, and then BaCl2, which will be an aqueous salt. It'll be dissolved in there. So when I look at this, what I really need to find out is how many moles of BaOH2 did I use? So I take the 0.2 moles times the 0.025 liters, and that's where I got my 0.005 moles from. And then I look at my molar ratios in the equation, and I see that it's 2 HCl's for each BaOH2. So I double that to 0.010 moles. And then I look at the strength of HCl, and if it's 0.010 moles and 1 liter contains 0.2 moles, I can divide by that, and that's where I got the 50 centimeters cubed from, or 0.050 liters. Number 5, you can see that I goofed this up initially. What amount of oxygen in moles? It contains 1.8 molecules. So since I have molecules and I want moles, I should take my 1.8 times 10 to the 22nd molecules, and I should multiply by the 1 mole over Avogadro's number. That's the other way of thinking of this. And so when I divide, I end up with the 0.030 moles. Number 6, which of the following contains the greatest number of molecules? A lot of you did this just the opposite. You went with the heaviest one instead of the lightest one. But think about this. The greatest number of molecules, something light means if it only weighs 50 grams per mole, I can have lots of them in 1 gram. These are light particles, but if it weighs 152 grams per mole, I can only have a few particles. So a lot of you seem to be using the right reasoning. You have to look at the molar ratios, but it's the lightest molar mass means you have the lightest particles. So if you have an equal mass of each one, then A, CH3Cl, would contain the most. Number 7, what is the empirical formula of a compound containing 50% by mass of element X with a molar mass or atomic mass of 20, and 50% of element Y, which has an atomic mass of 25? So if you have 50% of each, think of it as 50 grams of each, and I just converted each one to moles then. 50 grams of something weighing 20 grams per mole is 2.5 moles, but 50 grams of something weighing 25 grams per mole is 2 moles. So my ratio is really 2.5 to 2, or 1.25 to 1. Either way, I need to get this to a whole number. So the simplest whole number ratio for this is X5, Y4. Number 8 says, on complete combustion, a sample of a hydrocarbon compound produces 1.5 moles of carbon dioxide and 2 moles of water. What's the molecular formula of this hydrocarbon? So I wrote a balanced equation, and I knew it should be 1.5 moles of CO2 and 2 moles of H2O. So then if I look back, that means that my starting reactant had to have had 1.5 moles of carbon in it and 4 moles of hydrogen in it, because that's what shows up on my reactant side. And since C1.5H4 isn't a proper compound, I doubled that to C3H8. Number 9 asks, what will happen to the volume of a fixed mass of a gas when its pressure and temperature in Kelvin are both doubled? So remember, the relationship is P times V over T. So I just wrote in what I'm changing. The pressure is doubled, so I put 2 times on the top. Temperature is also doubled, so I put 2 times on the bottom. So you notice 2 over 2 will cancel out, so there will be no net change overall. And number 10 wants to know which contains the smallest amount of H plus ions. Well, the first thing I looked at is to see if they're all the same substance. I have HCl, but then down in D I have H2SO4. So H2SO4 is going to have twice as many H pluses in it. So 10 centimeters cubed of H2SO4 will exceed 10 centimeters cubed of HCl. And then 20 centimeters cubed of HCl obviously will have more than just 10 centimeters cubed. And then finally, the last thing to compare is the strength of it, and 0.5 molar will have twice as many as 0.25 molar. So I went with 8 because it's what we call monoprotic acid, because it only has the 1 hydrogen in it. It's the smallest volume, and it's the smallest concentration. Number 11, you are given the balanced equation for the reduction of iron ore to produce iron. You're told you have 30 kilograms of iron oxide and 5 kilograms of carbon. Heated until no further reaction occurs. Calculate the maximum mass of iron that can be obtained. So really what you have to do is find your limiting reactant. So I first converted my kilograms to grams, and then converted it to moles of each, and I had 187.5 moles of iron oxide and 416.32 moles of carbon. But I then have to convert and predict how much product each one can make, and I see that Fe is indeed my limiting reactant. Fe2O3 is my limiting reactant. So now that I know I'm going to be limited to 375.7 moles of iron, I can go ahead and multiply by the atomic mass of iron, and I should expect to get 20,980 grams or 21 kilograms of iron. Number 12 told you have an organic compound that contains 62% by mass carbon, 24.1% by mass nitrogen, and the remainder is hydrogen. So 62 and 24 is going to be 86.1. So I figure out that the other 13.9% is my hydrogen. And then to get my empirical formula, I need to change these percentages to moles, because these are mass percentages. It says 62% by mass. So I assume each one is grams out of 100. 62 grams of carbon then is 5.16 moles. 24.1 grams of nitrogen is 1.72 moles. And 13.9 grams of hydrogen is 13.8 moles. And so then I divide each one by my lowest molar amount, which was the nitrogen, 1.72. And that's where I get the whole numbers 3, 1, and 8, or an empirical formula of C3NH8. To find the term relative molecular mass, they were looking for a couple things there. First of all, you have to know it's an average mass of 1 mole of molecules, and then the term relative means compared to something, and in this case, it's compared to carbon-12's mass. And then the third part of the question, the relative molecular mass of A is 116. What's the molecular formula? Well, my empirical formula, C3NH8, would have a molar mass of 58.12. And so when I compare that to the experimental molar mass of 116, I see that the actual mass is twice as much, so the actual formula is also twice as much, or C6N2H16. Number 13, this was a difficult question. I included it just to show you that if you just take a deep breath and write out what you know, a lot of these questions that seem overwhelming at first really aren't as unsolvable as they appear to be. So I've got hydrogen gas going in. That makes H2 a reactant. I've got oxide of a copper in a dish. So I've got CuXOY, so some kind of copper oxide. I have excess hydrogen burning. Well, that's still a reactant. It's just making sure that any excess reactant goes away. And it says an oxide of copper was reduced. What that means is I've got just a single replacement reaction going on here. I should be getting H2O and copper metal. So that's the basic process that's going on. Hydrogen gas is being combined with a copper oxide to produce water and copper metal. So looking at the questions, it says, after heating, the following results were obtained. So first explain why the stream of hydrogen gas was maintained until the apparatus cooled. The reason why is so that no air would re-enter the test tube, because if air comes back into the test tube, then the copper will start reoxidizing with the oxygen that comes in. B said, calculate the empirical formula of the oxide using the above data. So even if you really didn't understand what's going on, you should have been able to see that 21.75 minus 13.8 was going to give you the mass of the copper oxide, and then the 20.15 minus 13.8 is going to give you the mass of the product, in this case copper, and then the difference gave you your mass of your oxygen. So then when I convert the 6.35 grams of copper and the 1.6 grams of oxygen to moles, I see I have equal amounts of each, 0.100 moles of both copper and oxygen. So my empirical formula is just CuO. And for part C, write an equation. Now I can actually balance my equation now that I know the copper oxide is just 1-to-1. And so my balance equation is just CuO plus H2 yields H2O plus Cu. Part D wants to know two changes that would be observed. So this has to be something you can see. You would see the oxide change to an orangish color metal, because copper has a very characteristic color. And you should also see water vapor or steam in the tube. Okay, since our product was copper metal and water, those would be the two observations we could make. Number 14, this is another neutralization reaction. Actually, it's a double replacement reaction. But again, a common one where they expect you to use some stoichiometry and a balanced equation to solve it. So 0.502 grams of an alkali metal. So alkali metal means it's in group 1A. If it's with sulfide, it's going to make it M2SO4, because 1A just has one valence electron. It's dissolved in water, so it just means it's aqueous. Excess barium chloride would be BaCl2. Added to precipitate all the sulfite ions as barium sulfate, so BaSO4 is going to be one product. And so then by default, the other product is going to have to be MCl. And we know it's just going to be 1-to-1, the metal to the chlorine, because it's a group 1A element. So calculate the amount in moles of barium sulfide. Well, they told you it was 0.672 grams of barium sulfide, so you just have to come up with the molar mass of barium sulfide, 233, approximately 0.4. So that's where I got the 0.00288 moles of barium sulfate. So then when I know the amount in moles of the alkali metal sulfate present, well, you have to look at the molar ratio. So if you hadn't already written a balanced equation, you needed to at this point. And you see it's 1-to-1. So it's also 0.0028 moles of my metal sulfide. And then letter C was actually far easier than a lot of you made it. Determine the molar mass of the alkali metal sulfate and state its units. Well, I know I had 0.502 grams to start with. I know it was 0.0028 moles that I started with. So I just take my mass, divide by the moles, and I get approximately 174 grams per mole as my molar mass. So the identity of the alkali metal, well, this is a little trickier because I know that it was 174 is how much M2SO4 weighs. I know SO4 weighs 96.066 grams per mole. So if I subtract that, that means the other 38.99 grams per mole is my metal. But then when I look at my formula, I see that I have 2 moles of my metal atom in each formula unit. So the 77.9 that the metal weighs is for 2 units. So I divide that by 2 and I get a relative molar mass of 38.99 grams per mole, or potassium. And I think it's kind of fun they had you write the equation here, but substituting in K for M, it would be the same equation as I wrote at the beginning. K2SO4 plus BaCl2 forms barium sulfate and 2 potassium chloride.